Hello, I am Matt Gadd, a postdoc at the Oxford Robotics Institute, working with Professor Paul Newman in the Mobile Robotics group. This work is in collaboration with Stefan Saftescu, Daniele De Martini, who will be taking part in this presentation later, Dan Barnes, and Paul Newman. We're all researchers at the ORI, and as a joint collaboration between MRG and A2I, the Applied Artificial Intelligence Research Group, the contribution to this work draws on experience from both mobile roboticists as well as machine learning specialists. We'll all be available offline to answer any questions you may have, but let's get started. This paper is about robust, large-scale topological localization using Fmcw scanning radar. The Fmcw class of radar offers a new level of robust sensing to autonomous vehicles in that it is inherently robust to poor weather and a lack of illumination. This is extremely promising for enabling vehicle autonomy, especially when considering how clutter and weather adversely affect cameras and LiDARs. However, while place recognition is well studied for cameras and LiDARs, it is not being applied to this class of radar. So the background in our institute for this project was a grant awarded to our university and Navtech, an Fmcw radar manufacturer. So during this project, we wanted to investigate the use of radar for all autonomy-enabling tasks, including motion estimation, localization, which we'll talk about today, and general scene understanding. So that kind of sets the scene for this work, and I'll now hand over to my colleague Daniele to explain our system.
Thank you, Matt, for the great introduction. Hello everyone, I'm Daniele De Martini, and I'll walk you through the methodology behind this work. Because of the conditional robustness of radar, our design philosophy is such that we want to map an environment once, and then use that map for repeated long-term localization of any further data. To achieve this, the map is encoded as a set of points in a learned metric space, which is discretized and then queried for similarity to live scans. You might recognize this autonomy operational paradigm as teach and repeat. Importantly, since the radar has a complete horizontal field of view, we wanted to build a localization system which is completely robust to the heading of the sensor. We'll go over these design decisions in a few slides. To catch this in an actual robotic system, I should mention that our vision for future deployment involves verifying these location hints with a downstream process such as scan matching. We start with a well-known VGG16 architecture for feature extraction and a VLAD core aggregation layer for learning image descriptors, which are good for place recognition. We build in circular padding, anti-aliasing Gaussian blurring, and azimuth-wise max pooling to provide invariance along the azimuth axis. Circular padding along the azimuth direction has been applied to each convolutional layer of the VGG architecture. This is done as the polar representation of the assembled FFT returns as no true image boundary along the azimuth axis. The operation brings equivariance to rotation to the feature extraction architecture. The downsample operation leads to high-frequency components of the signal, in this case the radar image, to cause aliasing in the sampled one. For this reason, we apply Gaussian blur to each downsampling operation in order to reduce this apport and help the natural equivariance of the convolutional operations. Lastly, we apply a max pooling operation along the azimuth dimension at the end of the feature extractor. Indeed, so far the architecture has only been equivariant to rotation, meaning that a rotation in the radar scan would apport a rotation in the output features. Applying a max pooling operation, which is inherently invariant to the order of the inputs, would indeed bring this invariance to the architecture itself on the dimension of the application, in this case the azimuth one. Without that augmentation, and purely through these modifications, we learn a representation in which rotated versions of an input scan are mapped consistently to points in a metric space. Now I hand it back to Matt to show some of the results.
We validated our system with 34 arrays from the highly accurate 280-kilometer ground truth radar odometry dataset recently released to the community. We supervised our training procedure with online triplet mining, where true positives are within a 25-meter radius of an anchor node, and we add a buffer radius of another 25 meters before considering a location a true negative. We used a rather simple validation split for verifying that the system is learning, while our test split is specifically designed to be difficult as it consists of backwards traversals. But more on that later. And one pair of forays is reserved for training, while another 27 pairs, all with the same reference or map trajectory, are used for analysis. And over this map built with data not used to optimize the network, covering the entire route built with all splits, the average localization performance over 27 trials has been enhanced with our modifications. But inspecting the precision and recall with varying embedding distance thresholds, we see that parts of the route are more difficult than others to localize. So the unseen environment consists of a backwards traversal of a section of the route, which you can see as B here. And this can be seen in the SE2 ground truth matrix on the left as an off-diagonal dark region. In this sort of situation where we already see the power of radar for localization, because it has a complete horizontal field of view, so it really should enable us to detect loop closures in reverse. And the tailored modifications we make to the baseline network, as covered by Daniele earlier, this really ensures that the representation for scans taken in places like these are identical in the metric space, or as close to identical as possible. Indeed, in the test split during which the robot revisits the same street, driving in the opposite direction, the enhancement with our modifications is more evident. We'd like to remark that the test split of all forays has never been seen during training. In the middle, you once again see the SE2 distance as computed from our ground truth database. On the left and right, you see two embedding distance matrices for a live trajectory as localized against the map trajectory. The left one is for the original architecture, and the right one is for the rotationally-invariant architecture that we've proposed. In the dark areas of the right matrix, perpendicular to the diagonal, they correspond to the vehicle driving in opposite directions. In this next experiment, we randomly rotated the frames from the localized trajectories along the azimuth axis. And this kind of simulates rotational deviation from, say, a rigidly mounted sensor. Although we didn't expect the original architecture to perform well, because we didn't perform the corresponding data augmentation, it is evident that our modifications are nevertheless successful at rejecting rotational disturbances, which is exactly what we designed it for. So taking a look at the image on the right, most dropouts in localization during which the robot has to rely on dead reckoning, such as ego motion or wheel odometry, are smaller than 5 meters, with the worst failure being limited to only 20 meters. And this is just when using the single nearest neighbor. So yeah, just using the closest neighbor in the embedding space results in over 90% of the input frames for something like 240 kilometers of driving to be localized correctly. And random rotations influence these sorts of systems metrics by less than 1% of the baseline performance. So to finish off, I will mention some further related reading. The first paper listed on the slide leverages the learned metric space that we've been talking about today within a sequence-based localization framework, which you have probably heard of, called SeqSLAM. And if you haven't, then definitely check it out. The second paper is about metric rigid body motion estimation and localization with learned radar key points, and that's also being presented at this virtual ICRA. I'd really encourage you to check that paper out. And the third paper is about cross-modal satellite radar localization using style transfer techniques, which is also being presented at this virtual ICRA. So that's all we have time for today. We hope you enjoy your virtual ICRA. Please don't hesitate to get into contact with us, either by email, Twitter, or in the virtual Q&A with any questions you may have. Thank you.